So we'll discuss here wave optics. Now, the first person to suggest that light is a wave was Christian Huygens, and his principle was known as Huygens principle. So we'll talk about Huygens principle in a while. So Huygens suggested that light is a wave, and Huygens suggested also that light is a longitudinal wave and a mechanical wave also traveling through ether. And Huygens principle was this: various points on the wavefront acts as source of secondary wavelets. And the disturbance beyond the surface results from superposition of the secondary wavelets. So first I shall tell you what wavefront is. Wavefront is the locus of points in same phase. Suppose you have a wave, say a wave on the surface of water in a river. These are the waves, see, the crests and troughs. So here I will mark the wavefronts. This is a wavefront, this is a wavefront, this is a wavefront. See all the locus of points. See, I have joined the crests and joined the crests over here. So these are different wavefronts, and the distance between the corresponding wavefronts is lambda, the wavelength. And what Huygens suggested was that light is a wave, or rather let's go to the example of say on surface of a river or a pond. Say you have a stick in your hand. This is a stick, and you oscillate the stick. The stick goes up and down. So when the stick goes up and down, what happens? The water molecules, those are in contact with the stick, those also go up and down. So you know how we have created the wave in a string. So we have held one end of the string, and suppose you hold with your hand one end of the string, and the hand goes up and down. So this leads to, or this has led to propagation of transverse waves in the string. Similarly, there is a surface tension and cohesive force between the molecules of water. So when you oscillate such a stick in water, it's similar to having so many strings on surface of water. So it's like that. The basic reason why the wave has propagated in a string is the cohesive force, or so the attractive force between the particles on the string. Similarly, same thing happens with the particles on the surface of water. So there is a bonding between the surface particles on water, which leads to propagation of the wave. And from symmetry, if you look from the top, the wave will propagate in all directions. See this crest, so you have all these crests over here. So join these crests. Yeah, these are the crests, right? These crests you join, and another one, this one. So this is how. So these are the wave fronts. I mean, wave fronts joining the crests only, and that's the stick going up and down like this. So here, as you see, the stick is the source of the wave, and the wave fronts are traveling like this. Now, if you consider one particle on the wavefront, say this particle, I consider a certain particle here on the traveling wavefront, so this particle. So this particle also oscillates up and down. So if the stick can be a source of the wave, why not this particle? So that is why Huygens said that every point on the wavefront, see I am drawing all these points, every point on the wavefront is as good as the stick which has started the oscillation on the surface of the river. Huygens didn't say so regarding the stick. He said that so all points on the wavefront become secondary sources of wavelets. So all these particles, say this particle, this particle, this, all these particles are sources of wavefronts. So they also generate wavefronts. Each of them generate wavefronts like this. So this wavefront, what you get? So this resultant wavefront, this wavefront is the resultant of all secondary wavelets from the sources, rather from the sources. Sources means points on the wavefront, I mean the previous wavefront. So select this S1, S2, S3, S4 like this. So all this wavefront 1, wavefront 2, wavefront 3, wavefront 4 like this. Due to all this, you have this as the resultant wavefront. You have this wavefront as the resultant wavefront, and same way these wavefronts will continue. Now there is a serious question of the back wave propagating. Why this back wave? Because say you consider this point S1. So this point, say S1, right? So as it is acting as a source, it will propagate wave in all directions, right? So from this source, the wave will propagate in all directions. So why only this forward wave? Why this one? Why not a backward wave also propagates and negates? So all this forward and backward wave is messed up and there is no wave at all. So this was explained by Fresnel by a very complicated mathematical calculation. So Fresnel's calculation of the obliquity effect. So there was an obliquity factor F, he wrote by this 1 plus cos theta. So where theta, say the wave was propagating this way with a speed v, so this is the angle theta. So this is the obliquity factor rather, where v is the direction of propagation of wave. V is the speed rather, right? Now with this obliquity factor we know that, say from S1 is theta and this one angle theta, so the effectiveness of the wave front is determined by the obliquity factor. Just I will show you. Say this was the stick, this is the direction of propagation, say this is source S1, secondary S1 is the source of secondary wavelengths. So at the front point the obliquity factor is 1 plus cos 0, that is 2, and at the back end the obliquity factor is 1 plus cos 180, that is 0. So what happens, the strength of the wave front happens to be huge and decreasing this way. Strength is highest in the direction of propagation v. So this explained the impossibility of the back wave. However, Huygens principle explained the most important phenomena of the interference of light. So what happens? Say you have two such slits, S1 and S2. This was the experiment in 1801 by Thomas Young, known as the Young's double slit experiment. So I will not discuss whole of the experiment now, but the modified and the useful version of it is this. If you use a monochromatic light, suppose yellow light, and you have two slits and you have a screen here. Now you somehow say on the screen you see alternate patches of dark and bright fringes like this. By these peaks I mean that these are brightest. So this is the bright fringe, bright, dark, this is bright and dark, like this. These alternate patches of bright and dark. So if you see the screen like this, so on the screen you will find say a bright patch and a dark patch like this. Bright and dark patches like this. By the way, this dark to dark or this bright to bright, rather dark to dark or bright to bright, this is that is beta. Beta is known as the fringe width. or from bright to bright also you can say the fringe width beta. And the slits are actually like this. Say on a rectangular board you cut two line sources like this, so S1 and S2, and these sources S1 and S2, so S1 and S2 act as coherent sources of light. So I'll explain in a while what coherent sources means. Coherent sources means meaning of coherent is that phase difference does not change with time. Phase difference between the waves does not change with time. These are coherent sources. One way to make the coherent sources is like this. If you place a lens and like this, place a single point source at the focus of the lens, that will make this S1 and S2 coherent sources. Or see, in this case actually these S1 and S2 are in the same phase. Now why these dark and bright fringes? You know, now as you know from Huygens principle, this S1 and S2 act as line sources of light. So these are line sources, right? So S1 and S2 being the sources of light, at the point where you have bright fringe, see obviously the path x1 traveled by the light wave 1 from source S1 and path x2 from source S2, they are same. So x1 is equal to, see here x1 is equal to x2, so we get a bright fringe. So we will have a brief recap on that, the condition of destructive and constructive interference. Just I'll tell you that if path difference x2 minus x1 is equal to n lambda, the interference is constructive. That means say amplitudes A1 and A2 will give you a resultant amplitude of A1 plus A2. That is the meaning of constructive interference. While if path difference x2 minus x1 is n plus half times lambda, the interference is destructive. So it's like this, A1 here and A2 below. So you have A is A1 minus A2 mod of that. So that is known as destructive interference. There is a thing to do with the phase difference also. If you remember it, for constructive interference, the phase difference phi is equal to 2n pi, and for destructive interference, phase difference is 2n plus 1 into pi. What is this n? So this n varies from 0, 1, 2, 3, 4 like this. So n is an integer. So you can approach also like this for two sources. Just this is a shortcut way to approach. Say this is A1. Say there are say waves 1 and 2. Waves 1 and 2 with amplitudes say A1 and A2 interfere. So A is the resultant amplitude, or say AR is the resultant amplitude. So that is A1 and A2. This is phi, and phi is the phase difference. So that is the resultant amplitude AR. And obviously phi is 2 pi by lambda times path difference. These all things we have discussed during the topic of waves, but still it's worth having a brief recap of this. So this is the relation, phi is 2 pi by lambda times x2 minus x1, or you can say phi is 2 pi by lambda times delta x, where delta x is the path difference. So that is a way to remember resultant amplitude. So here, so it's pretty much like the vector sum. So A1 is root over of A1 square plus A2 square plus twice A1 A2 cos phi. And suppose IR is intensity of resultant wave, and say I1 and I2 are intensities of waves from sources 1 and 2. Then also we can write, as I is proportional to A square, so IR is I1 plus I2 plus 2 root over of I1 I2 cos phi. So for the extreme case, the constructive and destructive interference, I'll write for constructive interference, you know what is phi equal to? Phi is 2n pi. So A is A1 plus A2. So IR is, if you see here, root I1 plus root I2 square. And for destructive interference, phi is 2n plus 1 pi. Also remember, for constructive interference, cos phi is equal to 1. For destructive interference, cos phi is minus 1. And for destructive interference, as phi is this, phi is odd multiple of pi. So A is mod of A1 minus A2, and IR is root I1 minus root I2 square. So if in a special case, if A1 equal to A2 equal to A, and I1 equal to I2 equal to I, then resultant amplitude AR is equal to 2A and IR equal to 4I for constructive interference. And AR equal to 0 and IR also equal to 0 for destructive interference. So this is Young's double slit experiment. So S1 and S2 are the slits. In the 3D figure, the slit will be like this. Two slits cut on a cardboard, S1 and S2, and you have a screen. And on the screen, we expect to see these alternate patches of dark and bright light. So let's take a point P on the slit, screen rather. Okay, however, it's given that the distance between, so S1 and S2 is D, and the distance between the slits and the screen is capital D. And also apart from this, it is given that capital D is much greater than small d. That means the screen is very far away. Now let us consider the point P, and the angular position of the point P here is theta. And let us consider the light going from sources S1 to S2. So S1 and S2 are acting as independent sources of light, as from Huygens principle we know. So at P, what is the path difference? So x2 minus x1, that is S2p minus S1p. Now here we'll do an approximation. So this is S1 and S2, and P is very far away. So to find out difference in path, we will drop a perpendicular like this shown in the figure. So this angle is also theta. As see, these are, so as they are very far away, the screen is very far away, both the light rays we can consider having angle theta with the reference line, right? This red line is the reference line. So as this is, as the screen is very far away, we can consider parallel lines. So both angle theta, so this perpendicular, so the distance is d sine theta. So we can approximate this x2 minus x1, that is delta x, path difference, is approximately d sine theta. This is true only when this screen is very far away, and you can treat the light rays as parallel. That means what we have done is that drop the perpendicular on S2p from S1, and thus calculated the approximate path difference to be d sine theta. Now, so at P, we can write delta x is equal to d sine theta. So for constructive interference, that is bright fringe, d sine theta, or see, delta x is equal to n lambda, right? As phi is equal to 2n pi, so delta x is equal to n lambda. So d sine theta is equal to n lambda, that is sine theta is equal to n lambda by d. So n can be 0, 1, 2, 3. So therefore values of sine theta can be 0 and c lambda by d, then 2 lambda by d, 3 lambda by d, till it permits. So as fringes can be down also, so we can just put plus minus here. and also at P for destructive interference. That is dark fringe. Phi is equal to 2n plus 1 pi. That is delta x equal to n plus half times lambda. So sine theta is equal to n plus half times lambda by d. So that is sine theta is half lambda by d. We can add plus minus here because it's on down and up side both. Then plus minus 3 by 2 lambda by d, then plus minus 5 by 2 lambda by d, plus minus 7 by 2 lambda by d till it permits. So that is why we can say that there are these alternative patches of bright and dark on the screen. S1, S2, light coming from here. Now this point is known as central maxima. So at the central maxima, what happens? Phi is equal to 0. Phase difference is equal to 0. And you have alternative bright and dark patches like this. So these peaks denote the intensity of light. So for this central maxima, obviously sine theta equal to 0, and for the next maxima, obviously sine theta is lambda by d. For the next maxima, sine theta is 2 lambda by d, and so on. For this first minima, sine theta is half lambda by d. For the second minima, sine theta is 3 by 2 lambda by d, like this. Now one approximation we can make: if the slits if the fringes are very close, that is sine theta is small, obviously, or sine theta is very small, then we can write sine theta is approximately theta and also approximately tan of theta. Then we can approximately find the distances. So this is approximately this half lambda by small d into capital D, and this distance is lambda by small d into capital D, and so on. So this distance is twice lambda by small d into capital D, like this. So as you see that bright to bright distances are constant. So this, say, the central maxima, distance between central maxima to first maxima is that between first maxima to second maxima. So that is the fringe width. And same way that if you calculate the distance of the minima, I will write it here. So that is 3 by 2 lambda by small d into capital D, right? So only if the fringes are very close, then only we can regard fringe width. Then the fringe width beta is equal to, as you can see, lambda capital D by small d. What is the fringe width then? It is the distance between fringe width, the distance between bright to bright or dark to dark. Fringes. In reality, you don't have such thing known as fringe width, because it will be non-uniform. In reality, this will be non-uniform. If there are small fringes like this, in a small region you have so many fringes, so you have approximately uniform fringe width. This I am taking the brights only, so each of these bright to bright are beta fringe width. But that is not true always. That is not true. If the fringes are far separated, then obviously this is not the case. So as you go further, the distance will go on increasing between the fringes. So in reality, you don't have a uniform fringe width. Say this fringe width. So from central maxima, see, this is known as first maxima, right? For the first maxima, phi is equal to 2 pi, and that is the central maxima rather. Central maxima phi is equal to 0. Okay. By the way, that distance between central maxima to first maxima is not equal to the distance between first to the second maxima. No, never it is equal. Only if the fringes are small and the separation is very less, then only you can approximate as a fringe width. Else, it is not possible. And also, as see, S1 and S2 are line sources. So as you go far away from the line sources, say the second maxima, if it is far away, see like this. So the see the intensity of the light decreases here. And for the second maxima, see, it is closer to the slits than the first than the far away maximas. So central maxima is the brightest. So the peaks decrease. So as you go far away, the peaks decrease, because these slits S1 and S2 are line sources. And for line sources, for line source, the intensity varies as 1 upon R. If you remember, for point source, the intensity varies as 1 upon R square. What is R? Distance between source to the point where the intensity is calculated. So in a real Young's double slit experiment, one demonstration of the experiment will be shown. I will make a separate video on that. See, this will be the case. The peaks will go on, as you go far from the central maxima, the peaks will decrease, right? So that is the brightest. Central maxima is the brightest of all. And also the fringes are very close. Fringes are closer when it is near to the central maxima. And here, as you go far away, the fringes, they are not so close. They are far separated fringes. Now, this Young's double slit experiment was performed with monochromatic light, That means light of a single wavelength. Say we have used yellow light. Suppose we have calculated with a single value of the wavelength. But if this Young's double slit experiment is performed with white light, then what is going to happen? Then at this point of the central maxima will be a bright spot, a bright white spot, because it is common maxima for all wavelengths. Now the first maxima for violet is nearer than the first maxima for red. Why? Because red has highest wavelength, because lambda of red is greater than lambda of violet. That is why. So apart from the central white spot or band, so everything else will be messed up and you cannot see any interference pattern on the screen. So Young's double slit experiment is best performed with monochromatic light and best performed with red light also, because red color has high wavelength, so you can see the fringes well separated.